So I started talking a little bit about the motivating example for high-dimensional statistics, which was linear regression in high dimensions. So we had this regression model, and we talked about the fact that if you have the classical setting, then the dimension of the parameter vector beta, which we call d, that would be much bigger than n. Okay, so you guys can hear me, right? All good. Hello? Yes. Okay. Then the idea was, so if d is much bigger than n, then we have a problem. This is the setup of the high-dimensional statistics, and there are motivating examples. The difficulty is that this problem does not have a unique solution. Even if there's no noise, if I try to solve this linear system of equations, I would run into the problem that there are many betas that have the same or solve the same systems. We talked about this, the possibility, like different possibilities of dealing with this issue. One, or most of them, are about imposing some constraints on beta that make the beta identifiable. So the classical, it's not classical, I would say like neoclassical, by now classical approach is to assume sparsity. And we'll talk about this approach in detail after the first chapter. But there was another approach that came up. I think Luciano pointed it out, that you could also do like the minimum norm solution. Let's say, for example, the idea is that we could sort of solve, like for the minimum norm solution, beta of this system of equations. Or if you want, you can also do the normal equations. So instead of doing that, I could do argmin beta squared x transpose x beta equal x transpose y. Okay, this also follows from the set of equations, but these are the normal equations. These are the ones that you solve. So this is like a d by d matrix, right? So the system is square. The matrix is square, and if x transpose x is full rank in the classical case, then you can invert it. There's a unique solution, but in general, you can solve this, and we can call this the pseudo inverse solution. And this is the extreme case of the ridge regression. And I mentioned that this is not necessarily a good estimate in high dimensions. You can try to argue for yourself that, for example, the same for the ridge regression, you're going to have an error which is going to be proportional to d, because you're going to have some error pair coordinates basically of this size. That would look like the end of the story. I just wanted to point out that if you care about the prediction, so here you're doing a parameter estimation. So we care about the loss, which is the quadratic loss in terms of the parameter beta. But let's say if I care about the so-called prediction error. Anyone knows what the prediction error would be here in this problem? Prediction. Or sometimes called generalization error. So this is a different loss function. So what is the prediction error in this problem? Anyone can have a guess?
The prediction error for the pseudo inverse, or just in general for these least square type problems?
For the regression problem, basically. So let's say the prediction problem is that I want to predict the response. Why? I don't care about necessarily the right parameter. So if I just want to have a prediction for future responses, or let's say I observe the future x, xi plus 1, let's say, or xn plus 1, the next sample, and I don't know the response, I want to find the response for that. So let's say I had a sample size, and now I get a new data point for which I don't know why. So this is unknown, and I want to predict it. Right. I want to have a prediction. So what will be the prediction error here? Like a natural prediction error. So let's say if you solve this regression, how would you predict a new value or the response for a new covariate?
If you had beta, it would be the prediction on the column space of the data points in X.
So what would that be? So let's say I have this is a vector, right, in RD. So let's say I have an estimate beta hat. So I have the estimate beta hat based on the previous data. I have now this covariate. What will be my prediction?
Oh, I see. Just the inner product.
Right. Okay. So there will be beta hat times x n plus 1, or something like that. X n plus 1 the other way around. Right. So it's just this function you evaluated at the new data point for beta hat. So let's say if I have, I'm going to write it as, so I have y n plus 1 minus y hat n, which is going to be x n plus 1 transpose times beta, the pseudo inverse, let's say. I can look at this squared, and this is based on y I x I from 1 to n. So n plus 1 is a new sample, right? So these are independent. And I can assume, let's say, x and y are both random from this distribution. So this is called the prediction error or generalization error. This is different than this loss. This is a new loss, you can imagine. If we care about this, then things become rather interesting. So I'm just going to point this out. So there is a recent line of work. In particular, if you were interested, I would recommend taking a look at this paper, Benign Overfitting in Linear Regression. Peter Bartlett, Long, Lugosi, and Ziegler. They also cite a couple of recent results. So an issue, a mystery appeared in the deep learning community that was sort of elaborated or elucidated over some period of time, that interpolation would sometimes work well in prediction. So if these deep neural networks, they have a lot of parameters, they're over-parameterized, just like the linear regression that we are discussing. And you could argue that these gradient descent methods that they perform might be finding the minimum L2 norm solution to an over-parameterized problem, and they observed that they would do very well in prediction. So this paper tries to understand this and a line of work. So there's an interesting line of work here that they cite, and they try to understand exactly. So well, we're going to talk about the setup, but for example, not the setup, but so if you look at this paper by the end of this lecture, hopefully you understand, let's say, this page. So what they're looking at, as you can see, the prediction error. So this is so let's say y and x are new. So the data points, this is the prediction error for theta, and this is like the optimal. So the difference between the prediction error of theta and the optimal theta. This is called the excess risk, sometimes in the machine learning literature. So this part is constant. So as you vary theta, this is the part that matters. But this is going to be like bigger than or equal to 0 and 0 at theta star. And their setup sort of involves a little bit of an extension of the model that I mentioned, in which they allow the noise to be sub-Gaussian, which we're going to discuss. But then they have some interesting results. So they look at this minimum norm solution. You can see this is exactly the minimum solution subject to these normal equations. And then they ask what is the risk, the excess risk of this estimator. And the result is interesting. So they have a bound on the excess risk, and then they have a lower bound, somewhat matching lower bound. And the idea here is that you can see this excess risk sort of, most of the terms go to 0 as n goes to 0, but this term sort of blows up as n goes to infinity, it seems, which is reasonable. But there are cases where this sort of, depending on the eigenvalues of the covariance matrix, this could go to 0. And so there is a certain covariance structures for which they analyze this. So this k star depends on n. It's like a cutoff that depends on the sample size. And so this quantity could go to 0. And so this is an interesting result in the sense that for certain types of input covariance structure, even if you do overparameterization, even if you can't recover the actual parameter, let's say you can't recover theta star, but in terms of this prediction risk, you can still be consistent. So the prediction error could go to 0. So I might at some point talk about this. So the techniques that they use and the sort of setup is very suitable for this course because they talk about concentration inequalities, matrix concentrations, things like that. And by the end of this course, you should hopefully be able to read and understand this. So this and the subsequent sort of or related work is a good fit as like a starting point for project. So I may or may not talk about this later on more, but just keep in mind that's one possible line of work that you can take a look and build your projects around it. So questions, comments about this? No questions? Okay, so let me add it here, benign. If I pronounce correctly, benign overfitting. Linear regression. So this is a pointer to a line of work, recent line of work on this subject. Okay, so let's move on. So we have enough motivation to study high-dimensional problems, I guess. So let's start from the basics. So we'll build some tools that allow us to be able to analyze these set of problems. So we start from non-asymptotic versions of the CLT. So the CLT controls the deviations or provides control and deviations of sums of independent variables. Let's say 0 means independent variables, or averages from their mean. We want to make that a little bit more quantitative. We want to have bounds that hold for any sample size, let's say, rather than in the limit. And so the basic idea is to use, so we want bounds of the general form like this. So the expectation or the probability that x minus expectation of x is bigger than tau in absolute value is small. So these are called concentration inequalities. If there's no absolute value, these would be one-sided deviation inequalities. Some people like to differentiate between the two, but oftentimes if you have one-sided inequality, you can turn it into a two-sided inequality easily. Sometimes not, but we'll see most often for the classes of variables that we look at, we start with one-sided inequalities and then upgrade to the two-sided inequality. So the basic building block is the Markov inequality. So if you have a non-negative random variable, the probability that x is bigger than t is less than expectation of x divided by t. So this shows that this tail probability is going down like 1 over t if the expectation is finite. So if the expectation of x is finite, then this is going to be all 1 over t. So there is a drop in the probability as you move into the tail, but this drop predicted by the Markov inequality is rather slow. And the reason is that you only require the first moment to exist. So any random variable whose first moment exists, I should say expectation. So the value is finite. For this bound to make sense, this has to be finite. And there are many variables for which this applies. Anything that has finite mean has at least this decay. Now, if I know more, let's say I know, so for the proof, you can try to prove it yourself. I'm not going to prove it, but you're welcome to try or take a look at it. Any probability book. The basic idea is just a very simple observation that this indicator is less than x divided by t. And then you would take the expectations, and this holds all, just like a one-line proof. The Chebyshev isn't like an upgrade or like a strengthening of this, and it says that if the random variable has finite second moments, and if I let the mu be the expectation, then the deviation of x from its expectation can be controlled. The probability of deviation can be controlled by the variance of x divided by t squared. And you can see the variance is here is finite by the assumption. And so this behaves like O of 1 over t squared, which is going to 0 faster than 1 over t. And so if you have the finiteness of second moment implies that the tails go down faster. So you could find random variables that make this tight. So there are random variables that have, so this cannot be improved for, I believe, for random variables that have only finite first moments. And this cannot be improved similarly if you just assume second moments. There are cases that go as slow as 1 over t squared. And so if you, so let me just point out the proof of this. What is the proof of the Chebyshev inequality? Anyone? How do you prove this?
It's Markov with x minus mu squared.
X minus mu squared. Okay, right. Sorry, let me organize a little bit here. So apply this with x minus mu squared. This is a non-negative variable, right? And this side would be the variance, right? And I have to put t squared here. And then if you take the square root of both sides of this, you'd get this, assuming the t is non-negative. So this is just an application of the Markov inequality. Everyone happy with this? Okay, so I can repeat this if I have the Peat moment finite. Then similarly, I can apply it to, instead of x minus mu to the 2, I can apply it to this to the k and use like Markov with this and t to the k, and then take the square or the kth root. And what we get is some sort of a bound like this. And you can see that here, because this is finite by assumption, this is going down like O of 1 over t to the k. So it's a faster polynomial decay. And so that gives you a sequence of tighter and tighter bounds. So what if I have, oh, so is it clear so far? So what if I have all the moments finite? Can I get a better bound than any of this? Is there a way to get a better bound? Anyone? So if I have all the moments finite, I have this for all k. And these may not be all. So it's not the case that if I write it down for different k's, the larger k's are necessarily better. This is not obvious. And so what I can do if so all moments exist, I know that this holds for any k. So what I would do is I find the infimum or minimum over all k bigger than or equal to 1. So the k equal 1 is Markov, and the rest, that's the 2 is a Chebyshev, and so on. So that's the technique that you usually do when you have many bounds. Here I have multiple bounds with this free parameter k. So I would try to optimize over k. So I find the best bound, and the best bound is the smallest one because I wanted to make this tighter, the closest to this. And so this gives you a bound which is hopefully better than any single one of them. And in fact, there's a homework problem in your book that argues that this bound is going to be better than the exponential bound that we're going to talk about. So it's worth checking out. But the classical, more natural approach is what we're going to discuss. If you have all the moments, then you can do something else, which is simpler than this. So this is not easy to compute in closed form. And we'll do something else. So in order to understand why we can do better than these simple polynomial decays. So any questions for that? So in order to do that, so consider the Bernoulli 1/2, and then look at the sums. So Bernoulli these are IID, a sample size n from a Bernoulli 1/2. This is like a coin flip, fair coin flip. And the sum is just the number of heads. And so the central limit theorem gives you something like this. So you subtract the mean of Sn divided by the standard deviation, which is this. And this converges to normal with mean 0 and variance 1. So what this suggests is that this side is roughly distributed as standard normal. So if I say that the probability of, for example, Zn is bigger than t, this is roughly the same as the probability of a Gaussian being bigger than or equal to t. So G is a standard Gaussian. And if you rearrange this guy, you would get something like that. This side, of course, is easy to show. That probability of this is, there's a closed form for, like there's a, not closed form, but there's an integral, but there is this also simple argument that can show that this is bounded by this exponential decay. And so you can see this is decaying much faster in t than any of these, right? So 1 over t to decay decays much slower than e to the negative t squared. This goes down very fast. And so if I rewrite this as, so let's say take t to be alpha root n, so I get a bound like this. So this is approximately less than or equal to this. And you can see that the n appears here. So if I set a like an alpha, for example, small, let's say 1/2. If I take alpha to be 1, or let's say 0.1 if you want. So this is saying that Sn is being bigger than n over 2 times 1.1. The probability is going to be like 1 point, is going to be 0.1 to the 2 divided by 2 times n. So this probability is 1/2 e to the negative n times 0.1 to the 2 divided by 2. And so if n is like 500, this is sufficiently good, or let's say 1,000. This is a very, this is like e to the negative n divided by 200. So if n is 1,000, then this is small, e to the negative 5, let's say. And I get an interesting high probability bound. So with high probability, but this is actually small, so the probability that this is less than this guy is going to be bigger than approximately 1 minus this, or 1 minus this, which is close to 1 if n is large. Right, and you can do it for the other side. And for example, you can get that Sn belongs to, let's say, 0.9 times 1/2 and 1.1 times 1/2. It's a very tightly concentrated around 1/2 with a probability bound that you can control. So you can see this holds with probability 1 minus like epsilon, and epsilon you can calculate. So these are the things that we would like to do. So is this calculation roughly clear to people? Some things like that we would like to say that Sn is like between 0.9 and 1.1 of the expectation, which is, this is Sn divided by n. Sn divided by n. Something like that. Okay. But there's a problem that this is not regress. And so this is not an inequality. And in fact, you can show that the difference in this approximation, so you're approximating this with this, the difference in the approximation is much bigger than this guy, or much bigger than this guy. And this is the so-called Bayesian type result. So you can show that the quality of the approximation in the CLT is controlled, let's say, by the third moment, and then divided by root n, the third moment of one of these. And so the deviation is of the order of 1 over root n, and this bound is tight, cannot be improved. There's a little bit of argument here. So this is from the HTTP book, basically. So if you look at this example here, you can see that, for example, the probability that Sn is equal to n 1/2 is roughly 1 over root n. But the probability that G, for example, is from this type of bound, you can get that the probability that Zn is in any interval minus the probability that G is in the same interval is bounded like this. And if you make the interval very small, around n over 1/2, so n times 1/2, then you can argue that this has to be close to the probability that G is almost like equal n over 2, but G equals n over 2, the probability is 0, while this probability is 1 over root n. So you can argue that this is tight, so you can make it smaller than this. So the conclusion is that the approximation error, which is n to the negative 1/2, or n to the negative 1/2, is much larger than this side that goes like exponential in n. So this is exponential in n, which is much smaller than this. So I have two error terms. One, the error of approximation, the other, the size of this. And the size of this, so you have this plus O of root n. So this is going to be O of root n plus this. And so you'd get O of n minus 1/2 plus O of e to the negative alpha squared over 2. And so this is going to be dominated by this because this goes much slower. And so your overall bound would be n to the negative 1/2. So this argument shows that the CLT is not strong enough to give us these finite sample bounds. So we have to look for a different approach. But we'd expect something to this, like this whole, but we can't use CLT to drive it. Does this make sense to people? Questions? Okay, so the solution is to do concentration inequalities directly, and the approach is to use the Chernoff bound, which is very useful in driving tail bounds. So the idea is that if I have random variable Zn, and I want to find the tail bound, this is or deviation bound, like this, I can take the exponential, so you multiply by lambda, which is positive, and then take the exponential. This does not change the nature of the inequality. So this is equivalent. So Zn being bigger than t is equivalent to e to the lambda Zn being bigger than or equal to e to the lambda t, right? So that's the equality here. And then I use the Markov inequality, right? So apply the Markov inequality. This is x, this is some, let's say u, and so you get the x here and then divided by u here. So that's my Markov inequality. And so the problem reduces to bounding this guy. And this guy is, if you recall, what is this guy? What is the name of this?
A moment generating function.
Yes, so that's the moment generating function of Zn, or the MGF. So that's the MGF of Zn. So the problem of Chernoff bounding, or the technique of Chernoff bounding, reduces to controlling the MGF of the random variable. Okay, so questions? And you can see if I can control this, the nature of the bound is like e to the negative lambda t. Let's say if this was not dependent on n, it's going to depend on n generally. But if it wasn't dependent on n, then the tail bound is like e to the negative lambda t, at least exponential in that fashion. Okay, so in order to move further, people have, over the years, have come up with some definitions that, let's say, encapsulate a class of classes of random variables. So depending on how the moment generating function behaves, you can define different classes of random variables, and then they would have the same type of tail behavior, the same type of concentration. So the basic one that came about is the so-called sub-Gaussian class. So the definition, most of these definitions can be made in terms of the moment-generating function, and then later there are equivalent versions that you can use. But let's say the easiest way to define these classes is by their moment-generating function. So a zero mean random variable x is sub-Gaussian with some parameter sigma if the moment-generating function has this satisfies this inequality, and it has to satisfy this for all lambda. And if the random variable is not zero mean, you just apply the definition to this. So x is sub-Gaussian if, in general, x minus the expectation of x satisfies, has this moment-generating function. The moment-generating function satisfies this for that centered variable. So the reason why this is called sub-Gaussian, there are many ways to see it, but from this definition, you can easily see that for a Gaussian random variable, this would be equality. So this side is the MGF of, you can call it the MGF expectation of e to the lambda z, where z is normal, which means zero invariant sigma squared. So this definition is saying that the moment-generating function of x is upper bounded by the moment-generating function of a Gaussian. So in that sense, it's below the Gaussian in that sense. So that's sub-Gaussian. So a Gaussian variable is by definition a sub-Gaussian random variable, but there are many other cases. So a random microvariable or a symmetric Bernoulli variable is a random variable that takes values plus and minus ones with probability 1/2. So this type of random variable is also sub-Gaussian because you can compute the moment-generating function. It's just 1/2 e to the lambda plus e to the negative lambda, and then you can verify that this inequality holds. This is a good exercise for you. And so it's random marker with some Gaussian parameter 1 at least. This parameter is not unique the way we defined it. So any sigma could work, but usually you want to find the smallest sigma. We'll talk about other parameters that are equivalent to this sub-Gaussian parameter. So any bounded random variable is in fact sub-Gaussian. So if x is in an interval a and b, almost surely then there is a homework problem, I believe, that you can show that 1 holds with sigma being b minus a over 2. So this is good to remember. There are different ways to get at it, but this is rather tight, if I haven't made any mistake writing it. You can prove that sub-Gaussianity with a higher value of sigma easier, but to make it this tight, you need to employ a rather careful argument, which you may see or may not see in your homework problem, but there is a homework or the exercise in the HDS, high dimensional statistics work, that you can take a look at. So this is very nice because any bounded variable gives you a very large class of random variables. So bounded random variables are sub-Gaussian. Okay? Questions? Let me ask you, how many people have seen sub-Gaussian random variables before? Did you see it before? Maybe raise your hands. No one has seen sub-Gaussian random variables before. Okay. Do you guys still hear me? Are you there? I see. Okay, let's see. There's a chat. Okay, good. Okay. So why this is useful? Because for any sub-Gaussian random variable, I can just plug that upper bound in this, and I immediately get a bound. And then I can optimize that bound. So If we do that, then we'd get this result that the probability that x is bigger than t for any sub-Gaussian variable is bounded by this exponential. And this is another way to see that things are sub-Gaussian, because that's how the tails of the Gaussian would go down. And so this is saying that the tails of a sub-Gaussian random variable are below the tails of a Gaussian with a variance that's the same as the sub-Gaussian parameter of x. So before proving this, the same bound holds. If I prove this, then I can just replace x with negative x here, and the same result holds. Anyone can argue why that would be the case? If I manage to prove this, I immediately also get another inequality with x replaced with negative x.
Negative x is still zero mean in sub-Gaussian.
Yes, great. Who was that?
This is Nick.
Nick, okay, good. Yeah, so if you go through this definition, rather, take a look at this. If x is sub-Gaussian zero mean, because this lambda can be positive or negative, and this side is just not sensitive to this sign, if I replace this with negative x, I can replace lambda with negative lambda, and it still holds. And so you can easily verify that a zero mean random variable is sub-Gaussian if and only if negative x is sub-Gaussian. So once we have that, we can apply it to the negative x. And so what I end up getting is I have the probability that x is bigger than t. Let's call this, I don't know, phi of t. This is less than or equal to phi of t. And I have the probability that negative x is bigger than t is less than phi of t. Then can I, from these two, conclude something about a two-sided deviation, or so-called concentration inequality? What will be the bound on this? That's the kind of bound that we're looking for.
Is it just 2 times the bound?
Why?
You just combine those probabilities on the tail.
That's right, but maybe a little bit of fill in the blanks. How do you? So this is true. So this is going to be bounded by twice phi t. After a while, you just this becomes second nature. But there is a little bit of an argument, like one line argument there, maybe less than a line.
The event that absolute value of x is larger than t is the union of the two events.
Okay, so this event is the union of two events, assuming you mean these two events, right?
Yes.
Right. X is, you can think of the x as, if you want, this is equal to the maximum of x and negative x. And the maximum is bigger than t if either one of them is bigger. So x is bigger than t, or negative x is bigger than t. And or is the union. And so the probability, this is the union bound. The probability of union is bounded by the, so this is like A, this is B, this is C. So the probability of A is bounded by the probability of B plus probability of C, because A is the union. So that would be the probability of x bigger than t plus the probability that negative x is bigger than t. This whole thing is less than 2 phi t. So once you do this once, then you can do it many times without doing the argument, but it's just good to remember. The argument is just union bound. Okay, so that's why in some of these arguments, it's easy to go from a one-sided bound to the two-sided bound. This relies on the fact that this definition of sub-Gaussianity is symmetric in a sense. So once you have something about x, you can have the same about negative x. This is not necessarily always true. Okay, questions about this? Okay, so So if you apply the Chernoff bound, that's the Chernoff bound. And I mentioned that, so you had this for many lambdas. So this holds for any lambda. And when you have many bounds, so you try to find the best, and the best means taking the infimum in this case. So it gets, if I want to write like mgf of zn value to lambda divided by e to the negative lambda, or sorry, it's just like e to the negative lambda t. Just do this, e to the lambda zn. And so that you can call this the Chernoff bound. That's the more appropriate version. The reason why you take the infimum because you want to be as close to the left-hand side. So this is an upper bound, so you push it down. You take the infimum. And so here we have it for x, and I just replace it with the upper bound that we have by assumption, right? And then we get this. And then the rest follows. You try to minimize this. It's equivalent to minimizing this, and this is a quadratic form. I'll let you minimize this for yourself. The result is going to be that. Okay, so that's how you get rid of the lambda. And the bound, this is the best bound out of the various versions that you have for different lambdas. Okay, yeah, it's interesting. So the individual bounds do not show necessarily a dependence like squared t, but once you optimize it, you get the proper bound. And this is how you apply it to get a two-sided tail bound. If mu is not let's say the expectation of x is mu and it's non-zero, then everything can be applied to x minus mu because of the way we define this. So x minus mu is sub-Gaussian. I just apply it now with x replaced with x minus mu, I get this bound. So that's the general bound for a sub-Gaussian. That's like a concentration of the sub-Gaussian variable. So concentration inequality for a sub-Gaussian variable. Questions? Okay, so this perhaps was not that difficult. Why this is useful is more because of this result. So if I have xi's that are independent zero mean sub-Gaussians with parameter sigma I, then the sum is sub-Gaussian and with parameter which is the square root of the sum of squares of the individual sigma i's. And the proof is rather simple because of the useful property of the MGF. So the MGF of Sn, this is just equal to the expectation of e to the summation xi, right? And this this is just the expectation of the product I from 1 to n, or just I for simplicity. You don't care about the number. E to the xi, and then this is equal to the product of e to the lambda xi. So why this is true?
Independence.
Yes. Okay, so this is by independence, and that's why the moment generating function is very useful. It turns, so the moment generating function of the sum, you can think of this like m, if you write it as more MGF. MGF of a sum is just the sum of MGFs. And so this property is the very useful property. Well, actually not the product. The cumulative generating function is like this. This is going to be the product of the MGFs. So, and you can see that the this side would be bounded by the product I e to the negative, or sorry, sigma squared I lambda squared divided by 2, and then this is just e to the summation sigma I squared lambda squared over 2. And if I call this sigma squared, you can see that this is this shows that this guy is sub-Gaussian with this parameter squared. Okay. So the key, that's the proof. The key is that the sub-Gaussian parameter behaves like the variance. So you know that the variance of a sum of independent variables is the sum of the variance squared, or not the variance squared, is the sum of the variances, right? So the variance of sum of xi is equal to the sum of the variances. And this is the key in many of the statistical applications, for example, that the law of large number holds and things like that. The variance of the sum like grows like n, right? So it's like behaves like O of n, not O of n squared. Because it's like you're squaring things, you get n squared terms, but the variance does not grow like O of n squared, which we would expect from a sum of, when you square a sum of n terms, deterministic, you'd expect to have n squared things, but the variance grows like O of n, which is the key in many of the statistical applications. And this is the case, so you can see the sub-Gaussian norm, or the sub-Gaussian parameter of a sub-Gaussian grows like O of n rather than faster. Okay, so if this is the case, then I can apply the previous bound to Sn, right? So Sn is a random variable. I'd get the probability, and then I can also, even if things are not zero mean, you can easily say that I can subtract the mean. That would be still, this would be sub-Gaussian because of the way you define it. So you'd end up with bounds like this. This is going to be bounded by e to the negative t squared divided by 2 sigma squared. So that's the tail bound, or the concentration bound that we have for Gaussian or sub-Gaussians. So you can get tail bounds or the concentration inequalities for the sum of independent sub-Gaussian variables that are exponential in nature. So that's what we wanted for the Bernoulli case, for example. So the Bernoulli example, so Sn being sum of xi and xi being IID Bernoulli is a special case because the Bernoullis are bounded variables, right? And so they're sub-Gaussian, and then you can write down a result like this for them. You can compute the sigma, and so sigma squared in that case would be n times the sub-Gaussian norm of Bernoulli 1/2, the sub-Gaussian parameter of Bernoulli 1/2. Okay. So this is very easy in a sense. We didn't need to work too much to get something about the sum. We just did it for a general sub-Gaussian variable, and then noted that the sum of independent sub-Gaussians is again sub-Gaussian with a new parameter, and then we just applied that result to this new sub-Gaussian variable. So this conceptually makes things much easier. So the introduction of the notion of sub-Gaussianity makes things much more, much cleaner, the arguments. Questions? Comments? Okay, so this is the same. So this is the one-sided bound, and you can again replace it with a two-sided bound and so on. But you get in the end something like that. This is called the Hofding bound. Hofding is like the classical bound, which is about, so if you apply this result to bounded variables, and then you use this, so you have, let's say, bounded variables each. So the classical one applies this to, it doesn't apply, it just directly proves it, but the classical one obtained, classical Hofding is obtained by applying this, apply this to xi being bounded, let's say ai pi, and then sigma I, the sub-Gaussian parameter, can be taken to be pi minus ai divided by 2. So apply it to this special case that would give you the classical Hofstede bound. For that reason, this is sometimes called Hofstede because it's like a natural extension to general sub-Gaussian variables. And there are sub-Gaussian variables that are not bounded. In particular, the Gaussian is an example. Okay, and then you can rearrange this in terms of the mean, so the average. So sometimes you write it as, so let's say I have IID variables. Or you don't need to have IID. Let's say I can just define the average sub-Gaussian parameter and then the average of the xi's, and then you can rewrite this. I can basically divide both sides by n here, right? And then call this, let's say u, right? Then t would be, so t would be n times u, and then I replace it here. So I get nu squared, right? And then this would be nu squared divided by 2 sigma squared, or u squared divided by 2 sigma squared over n, or the way I define it, this is just going to be 2 sigma bar squared. Okay, that's this. And then I can rename u to be t, so I get this bound. And so this is usually what you want to do. So this is showing you the average, and then I can put absolute values here and then put a 2 here. So this is showing that the average of zero mean independent random variables is very sharply concentrated around 0. So basically the probability that this guy is less than t is bigger than or equal to 1 minus 2 e to the negative n t squared divided by 2 sigma bar squared. And let's say sigma bar is fixed. Let's say their IID sigma bar would be just one of the sigmas. And so this goes to infinity. As n goes to infinity, this bound goes to 0 very fast because of the negative sign. So you'd get e to the negative. So let's say t is fixed. So if you fix an interval around 0, as n goes to infinity, this side is going to 0 very fast. So you get 1 minus something very small. So these are very, and then this holds for any n bigger than 1 and any t basically bigger than or equal to 0. So these are examples of finite sample / non-asymptotic bound that we look for. Okay, so the bound that holds for any sample size and gives you like a strict correct inequality, and it's not like asymptotic, there's no approximation here, and then you can use it to combine with other bounds to get like other bounds on different other quantities. So that's how we'll see how you manipulate these, but that's the basic example of a concentration inequality that we look for. The concentration basically comes from this n. As the sample size grows, the probability goes to 0 really fast. Okay, question? Okay, so there are equivalent characterization of sub-Gaussianity, and there is a bit of a difference between the high-dimensional probability book and HDS book. There is different methods of different like tastes of how to express these. I'm using the HDP book because that's a little bit more thorough, and it also emphasizes the idea that the constants are not that important that I want to sort of point out. So if you maybe just doubly point this out. So sometimes when you do these arguments, what matters is the order of things. So you care about this n, but this particular 2 might not be that important. So if you manage to do this bound with like 3 here, that will be good enough. This is a little bit contradictory because I said we care about explicit bounds and whatnot, but in practice, like in theoretical arguments, you really care about the order of things. So the tree here might not be that matters. And at the end of the day, once you try to combine these bounds, then keeping track of these constants becomes very tedious. So what sometimes you would do is you would say, oh, this, I don't care about this, and just put a constant here. So there's this bound holds with a constant. So I can say 1 minus 2 e to the negative some constant c, which you would say, for example, a universal constant for some universal or numerical. Universal means it doesn't depend on anything else, constant, or numerical. It's just a number, but we don't specify it. It's like 1/2 or something like that. And then if you manipulate it in a different expression, you get a different constant, you might still call it C. And so these C's could be different from occurrence to occurrence. And you see this quite often in papers when you read them. They might say that at the start of the proofs that the C's could be different from line to line. And it might seem like it's hard to keep track. It might be confusing, but after a while, once you get used to it, you'd appreciate the fact that you don't have to keep track of explicit constants. And if you make a mistake at some point, for example, you have to go back and fix every constant. But if you have done this, like the mistake is like buried in the like ambiguity of the argument. Okay, so this type of equivalence that's presented here is presented in that spirit, I would say. So so we had this, let's say, if the expectation of x is 0, we had defined subgaussianity like this. So the moment J function is bounded by an exponential of something, this we call the sigma squared. So there's a constant k5, let's say here, and this inequality holds for all lambda. But this statement is equivalent to, for example, the tail bound here for some other constant here. And the idea is that these two constants are related by universal constants. So for example, you've seen that if I had sigma squared over 2 here, the way we define it is with k5 squared being sigma squared over 2, then what I would get here is that 2 sigma squared, right? So, well, what I can say is that let's say k5 squared is 4 k1 squared or something like that. Or the other way around. Is that true or? Yeah, it seems to be true. So if you look at the HTTP book, for example, he says that these are, so what you care about is that k, let's say 1 is, there is a constant, let's say C1 or C, such that this is between C prime k5 and C k5. Okay, so there are universal constants. So these are universal constants that sort of control the relation of these two. So k1 could depend on the particular random variable, sub-Gaussian variable, but these constants do not depend on anything else. It's like 4, 2, 5. This holds for any this type of inequality. If you have this, then you have this for k1, which is like sandwiched between these two values of k5 with constant up to constant universal constants. And you can see, for example, here I can take it to be just 4. But that's the meaning of these equivalences. So if this holds, then I have this tail bound. So you have seen this side, like this implies this. But this is saying that this, if you have this for any t, then this also implies that. So if you're interested, you can take a look at the proof. And so this is equivalent. So tail bounds behaving like this for any t, they will imply this. But this one, for example, works even without the zero mean assumption. For this to hold, you need the zero mean assumption. So this is more general. So this is a characterization of sub-Gaussianity even if things are not zero, have non-zero means. The second equivalent characterization in terms of the moments. So this is called the Peat moment. This is the notation here. The Peat moment of a random variable is this guy. And this is saying that the Peat moment grows like root p. Again, there's a constant which is related to the previous ones by up to like universal constants. And this is how the moments grow. So if you want to, for example, prove that the random variable is sub-Gaussian, you can try to compute these moments and then show that they grow like root p. Or if you want to show that the random variable is not sub-Gaussian, you can compute these and show that they grow, for example, faster than root p. And so they can't be sub-Gaussian. And this has to hold for any not p bigger than or equal to 1. The third one is that the MGF of x squared satisfies something like that. So the MGF has to be bounded in the vicinity of, so this is the third one, and then the fourth is like seems to be a weaker version of the third. So this is like weaker. You start with 4, weaker version of 3. So 4 is the weaker version of 3. So it's saying that the MGF of x squared is bounded at some point. So the MGF of x squared is something like that. So this is saying that this is less than infinity for some lambda bigger than 0. And then you can translate it to this. If it's less than infinity, then you can make it be less than 2. The 2 doesn't matter here. But it's just equivalent to saying that the MGF is bounded. So why we don't say that this is bounded for lambda less than 0? So why do I want this to be bigger than 0? Why not lambda less than 0? Anyone? So that I know it.
Trivially bounded for negative lambda, since it's an exponential of a negative number.
Oh, can you say that again? Sorry.
It's trivially bounded by 1 for lambda negative.
Okay, great. Yeah, so if lambda is negative, then this side is bounded by 1. So this is always, MGF of x squared is always exists to one side of the 0. So at 0 or negative would be trivial. So this always is finite because the exponential is upper bounded. So that always exists. However, there could be no other point beyond 0 that this is finite. If there is at least one point here that this is finite, then it's going to have to be finite below it as well by just a simple inequality argument. And so it means that it's going to be like finite in the vicinity of 0. Okay, so this is equivalent to saying that the MGF of x squared is finite in the vicinity of the 0, but it's just you need one point to like the right-hand side of 0 at which to be finite. But interestingly, once you have this, then you also have, this is equivalent to the more stronger version that I can see first that it has to be like, it's going to be finite, and then there's an expansion. Near 0, there's some constant k3 that near enough to 0, then you can bound it by this. But this is not too difficult to show, given that you can expand this exponential in Taylor series. So if you're interested, take a look. Well, I would say the more important ones are the one that we talked about, tail bounds, the moment bounds, and this guy. This one is maybe sometimes useful. I haven't found any use for it yet. Questions?
Yes, Professor, I have one question.
Sure.
If we want to work with a tail bound after a sufficiently large t, so not hold for t greater than 0, maybe for some large constant,
Yeah.
could we require like a weaker version of sub-Gaussianity, or do we still, it is like the known way to do it, it's just going through sub-Gaussianity?
I'm going to talk about that. So you could relax the sub-Gaussianity, and then you could get tail bounds that would hold. It would be different. So we'll talk about exactly after this. We're going to talk about sub-exponential random variables, and they have this behavior that the behavior of the tail is different for small t and large t. But the sub-Gaussianity sort of, if you have it, it gives you a nice sort of quadratic exponential decay for all values of t. I'm not sure if I understood or answered your question.
No, yeah, that was good. I didn't know we were going to go into, yeah.
Right, we were going to go into more like more general classes. But yeah, so it could be possible that if you care about the large values of t, you could improve the bounds sometimes. But the things that I'm discussing here are a little bit more general. So for a general sub-Gaussian variable, you can't improve this for large t because, for example, the Gaussian is the sub-Gaussian variable, and this is basically the extent. So you can exactly control the tails of the Gaussian. And so for a Gaussian, there is no improvement. So this can't be going like e to the negative t to the third, for example. For large t, this is not going to happen. If you're restricting yourself to this class, but you could relax some of the assumptions on sub-Gaussianity and get like a weaker tail bound that behaves a different way, and that's a good like introduction to sub-exponential variables, which we'll talk about. Okay, any other questions? So at this point, this is interesting because this is equivalent, and again, once you have this for some k4, then you have the other ones for different k's that are all within some constant factor of the k4. And so this gives us a way to define another characterizing parameter for a sub-Gaussian. Instead of doing like for example, this one would be proportional to sigma. Here I can define a new parameter, which is the smallest k4 here, basically. So the smallest k4 for which this holds, I define it to be the sub-Gaussian norm. So the smallest, basically t, such that this bound holds. This is defined to be the sub-Gaussian norm, and then you can show that with this definition, this is in fact a norm. So this satisfies the axioms of norm. So for example, triangle equality holds for it, and it's like homogeneous, and then if this is 0, then it's only 0 for 0 random variables and so on. So it's a proper norm on the class of sub-Gaussian variables. And then because that would be like the smallest k4, then you can also show that this is going to be like within the constant factor of the other parameters, in particular the sub-Gaussian parameter. And we can also write every other statement here up to a constant in terms of this psi2 norm. So for example, because k1 would be sandwiched with constants within the constant factor of the Gaussian norm, I put a constant, unspecified constant here, and then the psi2 norm here. And then I replace this with a constant times the psi2 norm again. And this is going to be by definition the psi2 norm. There's no constant here, and so on. Okay, so you can translate everything. And for example, this is a very interesting result. This is showing that once I have a bound on, you can see that like xp, the Peat moment divided by root p, is bounded. Sometimes we write it like this by the psi2 norm. of x, and this notation just means there exists universal constant c such that this is bounded by this times. So I'd say let's say there are two quantities, for example, a is less than or equal to b in this fashion if and only if there exists a universal constant c such that a is less than or equal to c times b. And so you can hide the constants even. Once you have the ambiguous constant, you can sometimes hide them to avoid writing them. And so this is easy to remember. So this is bounded by the psi2 norm. So the psi2 norm controls these ratios of xp to root p, the Peat norm. Now for example, I can apply it with p equal to 2. P equal to 2, you get that x 2 divided by 2 is up to a constant bounded by psi2, or I can just drop the constant. The constant can be absorbed into this. So I'm saying that x2, the second moment, let's say this squared bounded by this. And so if this is zero mean, this is controlling the variance in terms of the Subgaussian norm is squared. So the variance of a random variable is controlled. A zero mean random variable is controlled by the Subgaussian norm squared. Okay, sounds good. So this is saying things like the things that I mentioned. So you know they're usually universal, numerical, absolute, constant. Sort of these are the same, have the same meaning involved in these calculations. So the Subgaussian parameter, for example, is within constant factor of psi2 norm. I would for example write I can write the this is up to a constant sigma x. And then something like this. I can also, for example, write an equality like this, where x infinity is just the supremum of the random variable. So this is, if you want to be really precise, this is like the essential supremum of x, or this is like essential because of the fact that we're dealing with random variable. But this is really the supremum of the values of the x. Omega is the underlying element of the sample space. So this is, if you have a bounded variable, this is finite. And so the fact that bounded variables are sub-Gaussian can be compactly written as the psi2 norm is up to constant upper bounded by the infinity norm of a random variable. So bounded random variables are, so if I have x infinity bounded, this means the random variable is bounded, then this implies that the psi2 norm is less than infinity. So this is saying that the random variable, so any random variable for which, so this is, I forgot to mention, x is sub-Gaussian if and only if the psi2 norm is finite. So you sort of translate this class, characterizing this class in terms of the size of a particular norm, which is very like common in analysis. So you like characterize certain class of random variables like L2 random variables or L2 functions. And here, this is a subclass. This is a much more, much smaller class of random variables. So for example, from this you can see that the L2 class of random variables, they're the ones that have finite second moments. The L2 class contains the, or this implies that the, let's say, sub-Gaussian class is inside the L2 class. So anything that's sub-Gaussian is L2. But there are random variables that are in L2, but not sub-Gaussian. We'll talk about that. Right, so these norm inequalities can be translated to inclusions of these classes of random variables. This is saying that, for example, the L infinity is inside the sub-Gaussian class. Okay, so if you take the L infinity is inside the sub-Gaussian class inside the L2. So it's somewhere in between. So in fact, it's like in L1 as well. Because I can do it with the L1. Or this is worse, so L2. And yeah, L2 is smaller, so LP. So this is going to be LP for any P bigger than 1. Okay, sounds good?
Professor, sorry, I have one last question.
Oh, sorry, you actually ran out of, sorry, I forgot. Sorry, guys, I think we're like 15 minutes over, right? I completely lost track of time. Yeah, so we have to stop here. Go ahead, yeah.
Yeah, so I just wanted to confirm. So for the question I had earlier for having a tail bound for large enough t, would that be
Yeah.
the same thing as having that finite norm, but except on the infinitum greater than 0, it'd be greater than that large t I'm working with?
That's an interesting point. I'm not sure. So you could, yeah, restrict this to like this. The question is that this might not be a proper norm anymore. It's worth thinking about. The fact that I managed to do this, then it might not be a proper norm. And whether then that translates to a different bound, I'm not sure. Yeah, it's worth thinking about, but I'm not sure that's going to be necessarily useful. Because once you define it, then there's going to be an infimum over all t as well. And so that is not necessarily going to change the nature of this decay. Yeah, but it's worth thinking about. I don't think this is necessarily going to be that useful if you do this.